In this video, we are going to start with integration. When we talk about integration, integration is nothing but summation or addition of really small values. Now let's take a function that gives me a graph something like this. Now if I want to know what is the area under that function between these two lines, I will take this point as A and this point as B. Now let's say this is my x and this is my function fx. Now if I want to know what is the area between this particular graph, what I will do is I will take a really small value dx at this particular point x. Let's say this is a point x. This width is nothing but dx. So really small width, and I can assume that this, because it's a really small width, the line here, the basically the value here is exactly same. So I can find that particular value. That value is, let's say, f of x. Now the area of this really small rectangle is going to be f of x into dx. Now this f of x into dx is going to be area of this rectangle. Now next, what if I do the same for the next value? The next value just besides it, I will find my f of x. Now that value is, let's say, x plus dx. So I will say that I will get the integration of f of x plus dx into dx, because the width I am again taking dx. Then I will take another small value, that will be f of x plus 2 times dx into dx. So similarly, if I add all such small rectangles from point A to point B, if I add them all, I should get the area under this particular curve. Now because this dx is almost equal to 0, we cannot actually find each and every value, because the area will again be almost equal to 0, and therefore we will not be able to add them, because the number of such values that we will get between 2 points are going to be infinite, because we are assuming that this dx width is almost equal to 0. So therefore we have another method to deal with this, and that is nothing but integration. So we say it is integration of our fx dx from point A to point B. Now this term is going to give us nothing but area under this curve. Now integration is not only used just to find area under the curve, it is very widely used in all different kinds of fields. Now I'll give you a simple example. Now let's say that I have a page. Now that page, whatever is written on that page, is going to be my fx. This page is represented by fx. Now the width of that page is almost negligible. I will write it as dx. The width of that page is dx. Now if I compile all such pages, the next page is going to be f of x plus dx, and its width is also going to be dx. And similarly, if I compile 200 such pages, I am actually going to get a book. So even though we assume that each page had no width or almost equal to 0, but when we compile multiple pages together with that width almost equal to 0, we still get a particular width. We can see this. So in this manner, I can say that page had only an area, it did not have any volume, but when I compile them together, I am going to get a volume. So this is one of the example integration can be used, but in our course we are only going to stick to our normal finding integration of our fx, any function. Now, like in differentiation, there are many methods in which we can actually find integrations. We have compiled a few functions whose integration we know. we are not going to go into how did we get that integration, but integration is basically the opposite of differentiation. So like if I had a constant value a, if I differentiate that, I got 0. So differentiation of a integration of 0 should give me a constant value. Then if I had x raised to n, if I integrate x raised to if I differentiate x raised to n, we got n times x raised to n minus 1. So if we integrate this n times x raised to n minus 1, we should get back our x raised to n. So differentiation or is opposite of integration, and integration is an opposite function of differentiation. Okay, so basically if I integrate differentiation of a particular function, we will say that is nothing but our function back. Or similarly, if I differentiate integration of a particular function, I should get my function back. So this is how we basically find our integration or differentiation. Now we have compiled a few formulas of our integration. So if I have a constant a, we will integrate and we will get ax plus c. Now we have written plus c because we can assume that this a had 0 added to it, and integration of 0 should give me a constant value. So we will write this plus c. So we get ax plus c. And similarly our x raised to n integration is x raised to n plus 1 by n plus 1 plus c. Again, because we are assuming x raised to n has 0 added to it, that is why we have plus c. Then for a raised to x, we have a raised to x by log a plus c. For e raised to x, integration is e raised to x plus c. Now log x, we do not have direct integration for log x, but because differentiation of log x gives us 1 by x, integration of 1 by x should give us log x plus c. Now whenever we are writing an integration, we have two types of integration, something called as indefinite integrals and the second is definite integrals. Now in indefinite integrals, what we do is we do not use the limits. So we'll just write our integration of this particular term. We don't know where are we integrating from and to what point. We are just finding what our integration function is going to be. And the second is when we know the limits, we are going from a to b. So our lower limit is written down here, upper limit is written up here. So that is called as definite integral, where we know definitely from what point to what point are we actually integrating. So whenever we have integration, we can have definite integral or we have indefinite integral. Now all the functions of integration written here are for indefinite integrals. Now in indefinite integrals, what happens is we'll say, let's say we'll integrate our x raised to 5, integration of x raised to 5 dx. Now integration starts with this integration sign and ends with dx. You should always write with respect to what value are we integrating. So this shows we are integrating with respect to a very small value of x dx. Now we'll say that is nothing but our x raised to n integration should be x raised to 5 plus 1, that will be 6 upon 5 plus 1, that is going to be 6 again, plus c. So this becomes our indefinite integral. Each of the indefinite integrals should have this plus c written in it. But when we say it's a definite integral, if I am integrating this value from, let's say, 2 to 9, my x value is going from 2 to 9. So whenever we are talking about limit, the limit is going to be of whatever variable we are integrating it with. So therefore, after writing this, what we will do is, we will say we will put now our limits 2 to 9. Now when we put our limits what we do is we say first we'll put our upper limit of 9 to our x and then lower limit of 2 to our x. So we'll get our 9 raised to 6 by 6 plus c minus we'll get 2 raised to 6 by 6 plus c. So we always subtract upper limit minus lower limit. So that is why we'll have minus sign here. Now when we subtract, you can clearly see this plus c and plus c will be cancelled out. So while solving in future, I am going to assume that we are going to use definite integrals. That is why I am going to skip writing this plus c. Our final answer is going to be a particular value. It is going to be whatever 9 raised to 6 by 6 minus 2 raised to 6 by 6. We can clearly see there is no c because it has been, the constant value has been subtracted and we are getting no constant values. So this term will be a definite answer to our integral. So going further, we are going to skip writing plus c. And this definite integral I'll explain again in the end as well. Now let's solve some questions. Now the first question, we see that we have similar type of numbers. We'll just take one into account. Let's say e raised to 5 log x. Now in this we know that if I have log x raised to a, I can take a outside and I can write this as a times log x. So similarly here I can write this as e raised to log of x raised to 5, and e raised to and log are inverse functions of each other. We know that e raised to log a should give me a, as well as log e raised to a should give me a. Remember, all the logs that we are going to see are always going to be log to the base e. So what I can do is I can write this as x raised to 5. Similarly, for all 4, I can say I'll get integration as x raised to 5 minus x raised to 4 upon x raised to 3 minus x raised to 2. Now in this case, what I can do is I can take x raised to 2 common from my numerator. So we'll get x raised to 2 and then we'll get x raised to 3 minus x raised to 2, x raised to 3 minus x raised to 2. So we are getting, this is nothing but integration of x raised to 2 dx. We know that if we have x raised to n, the integration is x raised to n plus 1 by n plus 1. So we'll get x raised to 3 by 3 plus c. Now because we are always going to see definite integrals, I might skip writing x plus this plus c, because what happens is whenever we are going to use definite integrals, this plus c is cancelled out. We'll see that in later. So I'll skip writing that plus c in each of them. So this becomes our first answer. We get x cubed by 3. Now for the second one, we have e raised to x into a raised to x, integration of e raised to x, a raised to x dx. What we can do is we can write this as ea the whole raised to x dx. Now we can consider this e into a to be a constant. So it will be very similar to our just a raised to x. For a raised to x, we have a raised to x by log a. So we will get integration of, so we will get ea the whole raised to x upon log of ea. For log of ea, we know that if we have two values multiplied, we can write this as log to the log e plus log a. So finally we can say this is e raised to x a raised to x upon 1 plus log a. So this is how we can solve this particular question. For the third one, we can write this as, now this is cube root, so it's cube root of x raised to 5. So I can say this is nothing but x raised to 1 by x raised to 5 by 3 dx, or you can say this will be integration of x raised to minus 5 by 3 dx. Now again we will take this minus 5 by 3 as our n, so we get integration of x raised to n. So we will get x raised to minus 5 by 3 plus 1 upon minus 5 by 3 plus 1. So that gives us x raised to minus 2 by 3 upon minus 2 by 3. Or you can say we will get minus of 3 by 2 into 1 by cube root of x square. So this is how we can integrate our normal functions. Now whenever we are having addition or subtraction while integration, we can give them we can individually integrate them. So in this case I can say this is our first one. We can write this as integration of x cube dx plus 5 times integration of x square dx, and also constants come out of the integration, minus integration of 4 plus I can say 7 times integration of x raised to minus 1. Okay, I forgot to write dx, and then plus 2 times integration of x raised to minus half dx. We can individually integrate this. So this is x raised to n, so we get x raised to 4 by 4 plus 5 times we get x raised to 3 by 3 minus integration of a constant is just ax, so we will get 4x plus 7 times. Now integration, now if you see differentiation of log x is 1 by x, so integration of 1 by x should give us log x. So therefore we get here 7 log x, and then plus we'll have 2x raised to minus 1 by 2 plus 1, or you can say just 1 by 2 upon 1 by 2. So you can write this as 4x raised to 1 by 2. So this becomes our integration. Now for the second one, what we can do is we can first divide it by x square. So we will get integration of x cube plus 7x plus 4 by x plus 1 by x square dx. Again we will give individual integrations, but instead of actually writing individual integrations, we can directly integrate it individually. So for x cube we will say we will have x raised to 4 by 4. For 7x we will have 7x square by 2. For 4 by x we will have 4 log x. Then for 1 by x square we will have x raised to minus 2. X raised to minus 2 becomes x raised to minus 1 by and multiply by minus 1. So we will get minus 1 by x. So this becomes our final answer. For the third one, we have integration of 1 plus x whole square. I can expand that I'll get 1 plus 2x plus x square by under root of x dx. Then I can divide by root x. So I'll get integration of x raised to minus half plus 2 times x raised to half plus x raised to 3 by 2 dx. Now again we'll integrate separately. For x raised to minus half, again x raised to n, that becomes x raised to minus half plus 1, so x raised to half upon half, then plus, for this we'll have 2 into x raised to 3 by 2 by 3 by 2, again x raised to n. For 3 by 2 also we'll have x raised to n, so we'll have x raised to 5 by 2 by 5 by 2. So if we solve this, we have 2 root x plus 4 by 3 root x cube plus 2 by 5 root x raised to 5. So this becomes our integration. And for the last one, again what we can do is we can expand that. So we have a plus b whole cube. So we can write that as integration. First we'll have a cube, so that becomes x raised to 6 plus 3a square b. So 3 times x raised to 4 into 1 by x square plus we'll have 3a square ab square. So 3 times x square into 1 by x raised to 4 and plus we'll have b cube. So 1 by x cube dx, sorry, x raised to 6, not cube. So when we integrate this, again we'll individually integrate. This x raised to 6 becomes x raised to 7 by 7 plus constant as it is. Then this becomes x raised to 2. We'll have x raised to 3 by 3. This becomes x raised to minus 2. So I'll say it will be 3 into x raised to minus 1 by minus 1. And this becomes x raised to minus 6. So we'll have x raised to minus 5 by minus 5. So final, we are going to get x raised to 7 by 7 plus x cube minus 3 by x and minus 1 by 5 x raised to 5. So you can represent that in many different ways. Here what we can do is we can separate our fractions and we can say we have 2 by 5 raised to x plus 3 by 5 raised to x. We can integrate them both with our a raised to x. We can assume our 2 by 5 is a and we'll get 2 by 5 raised to x by log of a, that is our 2 by 5, plus we'll have our 3 by 5 raised to x by log of 3 by 5. Next, for our second one, we can again integrate them individually. Our x by m is just a constant, x, we have x raised to 1. So when we integrate that, we are going to get x raised to 2 by 2. So x raised to 2 by 2m. Then m by x, we know that if we have 1 by x, we have the integration is log of x. So we'll get m times log of x. Then x raised to m, it is just nothing but our x raised to n. So we'll get x raised to m plus 1 by m plus 1, and lastly m raised to x is same as our a raised to x, so we get m raised to x by log of m. So this is how we can integrate some simple sums.